Um, Start to pick up here. And I guess, let's see, I'll share my screen. Uh, yes, let's see. I think that will work. Can everyone see that?
Yeah.
Can anyone see that?
Yes, yes.
Okay,
yes,
thank you.
I see it.
So so you've sort of done a little preparation for this, and so let's start off with any questions or anything you want to discuss before we based on what you've done in preparation. Okay, well I'll pick up here. As I said last time, this is our idea of some sort of basics to make sure that everyone from all parts of the heliophysics community has some core understandings. And the first question was why the Earth and the planets have ionospheres. The second one, which we're not going to discuss in this class, is why the sun has a corona and a solar wind. Sorry about that, but we didn't, even with 2 weeks, we didn't have enough time. And the third one is why do the Earth and planets have ionospheres and magnetospheres? I hope people got the correct slides. I tried to post a correction. I think the slide link on Slack was pointing to the old slides. Anyway, and this is as far from my own area as you can get. I study reconnection and magnetic reconnection and solar flares, but I do stand by the idea that really, as a heliophysicist, I should have some idea of how to answer this question. And here is a wonderful diagram that combines a few figures from the, we call it Principia after Newton's work, but it's the principles of heliophysics. And what you can see here is in the upper left is a wonderful color scale diagram which shows wavelengths of light. Altitude, of course, is vertical, so from the ground up into space, and the color indicates how much energy is being deposited at each wavelength. And you can see if you go above 3,000 angstroms, or 300 nanometers, I should stick with that, you do get energy going all the way down to the ground. And actually, this is not showing you what's absorbed at the ground. But anything short of that, you'll see there's just a white region where there is no deposition. And that's because the wavelengths have all been absorbed. So this is the beginning of the understanding of this process. It is the absorption of energy at these shorter wavelengths that the sun emits that is leading to ionization. And here's a nice view of the temperature structure of the Earth over on the right. And you can see, at least for the absorption of this, this long wavelength of all of these, sort of 2,500 angstroms and above, the deposition is what's creating this a hump in the temperature structure called the stratopause. And so the stratosphere, and then above it is the mesosphere. That's all being created because there's extra energy being absorbed in the atmosphere itself. Visible light is making it right to the ground, but the this light is being absorbed, and the other wavelengths are being absorbed even higher up, but there's less of them. And then the bottom figure is sort of the spectrum in blue of solar radiation against the same wavelength scale. I tried to match it up using PowerPoint, and you can see a black body spectrum at rough temperature of the photosphere. The sun sort of deviates from that, departs from that, but we do get a lot of emission down at these what we call extreme ultraviolet wavelengths, and 171 angstroms, yeah, that's right, or sorry, these are ultraviolet wavelengths. And then the extreme ultraviolet and the chromosphere, or the extreme ultraviolet and the X-rays, are coming from the sun's transition region and corona, which are not at 57 70 Kelvin, right? They're much hotter. And so the amount of emission you get there is way above what a black body spectrum would produce. And that's what is being absorbed way high up in the 100, 150, 200 kilometer regime. So it's really about the energy deposition and the ionization it creates that answers the first question, the ionosphere. So here, I think some people did this exercise here. Is that right, Nick? Someone did activity 9?
I believe so.
Yeah. So we asked to compute scale heights for, or you were asked, for the Earth, for Venus and Mars. This is the expression for scale height. Could someone just unmute and chime in with one of those 3 scale heights and that you found? I want to go back and try to compute all these things. I think.
Anybody from the Hawaii time zone group?
Oh man, is that the? That may be the problem here. So it's really, I mean, let's face it, it's not, it's just plugging numbers into a formula. You have to find the temperature of the atmosphere, the mean mass of whatever the atmosphere is made of, which is going to be different. The Earth is mostly, anyone? Earth's atmosphere? Stuff we breathe all the time? Nitrogen, yeah, nitrogen, N2. So nitrogen, I believe, has an atomic mass of 14. So you're talking about 28 times the mass of a proton. And then G is the surface gravitational field height. And here we go. Yeah, so particles are N2, so the mass is 28 times the mass of a proton. We all know the Earth's temperature is roughly 300 Kelvin. And everyone, for my freshman physics, we drill this into them. G is, and we have them use just 1,000 centimeters per second squared, right? We don't worry about the 9.8 stuff. We're just interested in understanding this. And the Venus, you have to figure out, oh, it's made of CO2 mostly. It has a gravitational acceleration a little lower, temperature a lot higher, and for, oh, sorry, I didn't do Mars over here. You should have done Mars, but here's an interesting version. The sun, because the same thing happens here, but of course it's much hotter, 6,000. G is a bit higher, but the mass of the mass is really just hydrogen atoms. Actually, if I wanted to be really good, I'd say that's half of this, because every other particle is a hydrogen, every other particle is an electron. But anyway, what we get for the scale height of Earth is 9 kilometers. For Venus, it's 15. And for the photosphere, it's 180 kilometers. So it's a much bigger scale height, but of course the sun is a much bigger place. So this just gives you an idea of how these atmospheres fall off. So this is the diagram, I think, I think it's in Principia, but it's certainly in volume 3 of the text. And it shows the density in number per cubic centimeter, particles per cubic centimeter of each of these species. And you can see N2 is falling off at roughly, so N2 is falling off. Well, here we're higher up. We're at 200, 300, 400. So the temperature's a bit higher. Okay, it's gone up really by a factor of 5. So the scale height has gone up by a factor of 5 or so, and it's falling off exponentially with this scale height of 43 kilometers. Hydrogen by itself, helium by itself is falling off much more slowly. So helium is starting to take over, and atomic oxygen is falling off with a scale height only 76 kilometers. So because its atomic mass is so much lower than some of these others. So this is really what you're dealing with in the region where the ionization is occurring. And you can see the electrons by themselves. This is not falling off at the scale height, right? This is really coming about a different way. It's coming about because the electrons are being produced by this absorption, and that is the ionosphere. So what we're really interested in is this component of the atmosphere, the electrons. I'll just point out, because I hope some of you got to see the total eclipse that crossed the United States. Those of you in the United States, it would be easier, in 2017. I don't know if anyone here was able to see any of the eclipses, say in Chile. I went and saw the one in 2019. One of the things that's amazing is how, I'll show you this, how quickly the moon just blocks out the sun. And this actually reads from, well, this is actually coming off of the sun. And you can see these little, what are called Bailey's beads. And this really comes about because the moon has rough features, and the solar surface is actually shining through some of these mountains and valleys and things. So you're like, wow, the edge of the sun must be really sharp. And indeed it is. It's 180 kilometers. I remarked, that's not very thick. I mean, sorry, that's very big. I wouldn't want to have to walk 180 kilometers in a day. But when you think about how big the sun is, really you're seeing an edge that drops 95% over 0.7 arc seconds. That's an angle that's too small to resolve by the human eye, way too small to resolve by the human eye. It's actually bordering on too small to resolve by a telescope on Earth without adaptive optics. So 1 arc second is kind of the best you can do on the best day at the best site. If you're under the Earth's atmosphere, and you can't resolve how thin the photosphere is. Okay, and the last thing I'll point out is when you see it, here's a picture my brother took. We were watching the eclipse in Oregon. The thing that strikes you, of course, is the corona. That's what I spend my life studying. But just knowing this, you could immediately see, oh, wow, the corona is not 180 kilometers thick. It's much thicker. It falls off much more gradually, right? And this doesn't take any kind of special instrument to know that, wow, the corona is extending really, really far. And so the people who first saw this were confronted with two options. Either the solar corona is much hotter than the photosphere, or, and I'm talking about 200 years ago, the alternative is, or it's made out of some stuff that we don't have on Earth that has an atomic mass much, much less than hydrogen. And there were many people who took that option. It seems actually logical. They found other elements they couldn't find anywhere but on the sun, one being helium. Helium is prevalent in the outer Earth's atmosphere, but it doesn't appear much on Earth. So it took a long time to find any. So they thought, helium exists only on the sun. So this new stuff, coronium, exists only on the sun. And that is what's building up the corona. We actually know now that there is no such stuff as coronium. It is made of hydrogen, and therefore really has to be much, much hotter. Okay, so that I just want to point out is a nice, very, very photogenic example of this scale height problem. All right, now let's see. I better check because we are kind of early here. Catherine, are we ready for some breakout groups?
Yes, we are.
Oh, we are. Okay. So this is activity 19. I definitely think some people have done it, activity 19. Why don't we break into our groups where hopefully some of you have done it in the group and you can help them along. If no one in your group has done it, I guess, just try to feel your way through it. This is activity 19. And it's basically to show that the optical depth, right, which is related to the number of collisions on average number of collisions on average you would have on the way down to a height h, and a sigma sub a is your cross section for collisions, n is the number of things you can collide with. H is the collision, is the pressure scale height, and chi here is the angle from the vertical that you're descending at. So this is the optical depth, and this is the heating produced at that optical depth, and heating produced, and then here is the expression they want you to derive. So let's break up into our groups and just try to take a crack at this, because this is really what's going to show us where this ionosphere comes from. Okay,
And Dina, we're at 20. Oh, I'm
let's
sorry,
give
we're at 20
everyone
minutes after.
10 minutes. What?
10 minutes.
10 minutes. 10 minutes.
I'm back at 30 minutes after the hour.
That'll be good. Thank you.
Great.
All right. Well, I guess I'll start.
When that time period date, it was
Now we're getting to the point where these things are happening way far north and south. I think there's going to be one in Antarctica soon. And then I had to go pretty far south in Chile to see it in 2019. I think after that, it was only visible in Patagonia, the 2021.
Okay, everyone is back.
Okay, welcome back. We all had a chance to do that, and I know not everyone was able to do it as well, but I'm going to call out someone from group 1 because I see group 1 really had it going. So could someone from group 1 just sort of tell us your reasoning here? Or you could share. I can stop sharing if you want to share something.
We were mostly writing it out and drawing the diagram of the angle and deriving tau. I don't think we got time to derive the whole thing.
Okay, but how about, yeah, I know other people went by combining these two, but just talk us through what you did to get equation 2.19.
Yeah, so we started with just the definition of the optical depth as the integral, the cross-sectional absorption area, and then the number density as a function of the path length. And then drawing out the angle entering the atmosphere, we figured out that we could rewrite the DL in the integral as some change in the height divided by the cosine of that angle.
Right. So that enters the denominator of 2.19 just through geometry, converting an integral along a path length that's inclined to the integral along the vertical. Yeah. And then the mysterious H sub P.
That was because the density is falling off as an exponential according to the, so it's whatever the density is at the ground, e to the minus height over the scale height there.
Right, right. Okay. And did anyone else then also manage to figure out how to get to the final equation there? Any thoughts on how that's done?
Let me try.
Oh.
Okay, let me try. I think the equation, to derive the equation QH, Q bracket is the
Right.
product of equation 2.19 and then equation 2.18 should actually lead us to. That is what I think it should.
Okay,
Yeah.
but you need an exponential of,
Yeah.
so you end up with the exponential e to the minus tau. And so,
Yeah, that we can use. I mean, we can use the radiative transfer equation.
oh
Derive
yeah,
that.
yes, you can. Right, which is essentially, okay, yeah. So that seems to be, that seems to have gotten at what I would have told you either, which is what you want to do is figure out how many times you're going to collide with something if you go through a certain path length. And here are all the little objects you could collide with, and each of them has a cross-sectional area of sigma A. And there is something in the radiative transfer equations, but also done in a lot of physics, where you answer that question by basically creating a different question, which is if I just look at the centers of these objects I could collide with, and imagine a cylinder around my path that has cross-section sigma A, it's the same as how many points are in that cylinder. How many, if I have a cylinder of a given length, how many of them have I captured? And that's the average number you're going to include, which is what we just heard about, sigma A N ds, right? That's the answer to that question. How many collisions on average would you suffer over a certain path? And that's where tau comes from. Now, since you have an average, right? You have the average number of things inside your cylinder. You want to ask, well, what if the average is 3, but really how often will I have made it that distance with 0 collisions? And here's where you have to remember that the average isn't the number, it's the average number. And so there's something called the Poisson Distribution, which is I always refer to say the number of customers that go into a store in an hour. If you know the average rate at which customers come in, at any hour, it's going to be different. And this is a probability distribution. And so the probability of the number n is the average number to the nth power over n factorial times e to the minus the average, tau. And so this thing here then tells you if I put n equals to 0, I just get tau to the 0th power, 0 factorial, which I am always amazed is 1, but it is 1. And then you just have e to the minus tau. So e to the minus tau is, and I think I put that in the beginning of that, it's in the setup, is the probability of suffering 0 collisions when the average number is tau. Okay, so that's where that comes from. And then you basically say the probability of survival is that, and then here's the thing that we were just talked through, the integral of sigma n, and n goes as, oh yeah, here is the diagram showing what we just heard. I put secant of chi instead of 1 over cosine, they're the same thing, etc. And so that's how you get tau. And then, oops, that's the same thing. The number, the heat you're delivering is basically the number of the energy of each collision times, oops, I thought I had that in here somewhere. Yeah, here's the probability of surviving. The energy flux at infinity is also going to fall off that way because that's how many photons are making it. And then you have to put in the number of the energy eta sub I with each collision. And that's how you get this expression, this final expression. Okay. So I hope that was not too baffling for people. It gives you some feeling for how this all works. And sorry, these are kind of out of order. So what that really tells us then is, depending on the cross section, you could have basically the fact that you're exponential, that you have an exponential inside an exponential. This always amazes me. When you plug all this in, what you've got is an exponential of n. Oh shoot, where did I put that? You have this expression here, which is an exponential of n, and n is an exponential. So I've buried my lead here. The coolest thing in the world, tau is an exponential, and tau goes inside the exponential. So you have an exponential of an exponential, which is just awesome. I think it's the only place I've ever seen that come up. And this is those kinds of curves look like this. They just fall. Your probability of surviving goes from 1 to 0 in a very short region, and you just hit the deck. So depending on what that cross section is, you're going to make it 150 kilometers, 100 kilometers, or 50 kilometers down to that depth. For a very small cross section, you make it far down. For larger cross sections, here is, and someone asked if the collision cross section is a constant with height. I've sort of assumed here it is, but it's not a constant with wavelength. Depending on your wavelength, you could have a very high probability of colliding. And so at wavelengths below, say, 50 nanometers, or around 50 nanometers, your cross section is 10 to the minus 17, and you only make it to 150 kilometers before you're gone, you're absorbed. And that's really where this big absorption, this high absorption area is. Then it falls off. It's kind of jaggy around here. This is where there are some resonances that really come into play. So it makes it extremely likely to absorb. Your cross section goes way up when you hit a resonance, and then it falls way down by the time you get even close to the visible. And that's why these these near ultraviolet photons can make it so far down to 50 kilometers or so to create the stratosphere. Their collision cross section is extremely low. You can see that there's basically 5 orders of magnitude difference in collision cross sections for ultraviolet, near ultraviolet photons and extreme ultraviolet photons, right? And that's really what gives us this kind of absorption structure here. And it's because you can't really make it out from the color table, but these things are just falling right to zero. Well, you can sort of make out that this white edge is really, really sharp. All right.
Hey,
Yeah.
Danny, there's a couple of things in chat. So I can read them to you. Cole is asking about the first one is Cole is asking about the top right panels.
Yeah.
So which wavelengths have you picked out for
I
those?
have not picked out wavelengths. I have picked out cross sections. I basically used this expression with a particular cross section.
So
I
it's
just
just
plug
whatever
in 10 to the minus 17, 10 to the minus 20, 10 to the minus 23. These are all values that occur, but you can pick out where that wavelength would be from the diagram in the lower left. Yeah, so I'm just saying this is just very much an educational exercise. You just plug in different cross sections to this formula and you get probabilities of survival that are very different. They all look the same and they just go to zero at different depths. And this is just another way I like to write that depth.
And then Claire, you want to state that out loud?
Sure. I was just wondering what the physical mechanism is for increasing the cross sections at those low wavelengths.
At the small wavelengths,
Yep.
That's an excellent question. It is the fact that you're going to be able to. It's not really a resonance, but you have ways of ionizing the atom, and that makes it much more likely that you're going to collide. If there's no excited state that the atom can get to with your energy, right? So there's nobody who matches your energy. They're not going to want to collide with you. And sorry for anthropomorphizing this quantum mechanical process, but that's really the way resonances work. And you do see in the jaggies, you see that this is where those resonances are first coming into play. You're maybe exciting into the first excited state and the second excited state and the third and the fourth. And if you remember, even for the hydrogen atom, they really pile up very quickly in energy. And pretty soon you've got a situation where you can knock the electron into whatever energy it needs to go into, because you have the minimum amount to do it. And so this is really just a result of ionization. You now have the amount of energy necessary to ionize those atoms. Some of you might know that, some of this absorption peak here, we have ozone, which is a 3-atom combination of oxygen, and that's not very natural. It's not a preferred state. So it actually is much easier to break apart. And so you get that kind of peak from ozone. Now there isn't much of it, but because it exists there, it is sort of prone to absorb those longer wavelength photons. And there must be some similar explanation. I can't remember what you're ionizing at 150 nanometers. Yeah, does that help?
Yes, thank you.
Yeah. Okay. So then that basically gives us this heating profile, and that's actually what's being plotted in the colors here, is how much energy is being deposited. It's all of the explanations we just went through here, your chance of being absorbed times the energy that's being absorbed. Okay, so if you plot then Q, that's the heat, it's basically the derivative of this probability, right? That's how much energy is being put out. And that's this red curve. So I've done it for exactly the same, just arbitrarily chosen cross sections. And this is what's known as the Chapman layer. Chapman was the first one to work out this theory. And these layers have this very sharp, hard bottom. And that's because of the exponential of an exponential. And they fall off. Well, this is a log scale. So they're still falling off exponentially with height on the top side. But the bottom side is crazy fast. And so the red is the energy being deposited for each one of these cross sections. And that's really where you get the energy plot here. So I'll keep coming back to that. So if you're good at imagining what these color tables look like as a graph, this slice here with a cross section of 10 to the minus 23 is kind of giving you this graph right along 250 nanometers, right? It's just zero, all white, and then it just shoots up to its maximum, which is again a sort of whitish. Sorry about that, and then it falls off more gradually on a log scale. And this is of course a log color scale. So that's sort of the shape of the ionosphere here. Okay. And this is what's really giving rise to these free electrons. This is why we get the electrons, because we are basically, you are having photons absorbed and knock you into some of these excited states. So this diagram says if you have oxygen and you hit the right energy photon, you will become oxygen plus. If you have nitrogen and you hit the right energy photon, you're going to become N2 plus, et cetera. And so that's where those things are: ionization of O2, atomic oxygen, and nitrogen. That's what gives rise to those jaggies. And that's also where you get all these free electrons. So when people tell you about the ionosphere, they're generally telling you about the free electrons. And so this is the density of free electrons you're going to see in the ionosphere as a function of height. And you can see that it really follows this area of the curve where you're absorbing in and ionizing rather than just knocking apart O3, right? Which is all fun and games, but it doesn't really give you any free electrons. It just creates more atomic oxygen. So it's above these heights, sort of 100-kilometer, a little under 100 kilometers and above, that your absorption of photons is really creating, is ionizing things and therefore creating free electrons. And so this is the ionosphere. And you can see, we didn't really talk about it, but that solar cycle that we did talk about is creating, at the peak, you have a much more magnetic field, and therefore you have a more extended corona, and the corona is what's creating these short wavelengths that are doing the ionization, these 100 nanometers and below. So during solar maximum, you get more ionization, you get more electron content. Especially during the day, that's when the sun is actually shining on you. And you can see here, there is, even at solar minimum, solar maximum, at the low heights, there is this day-night oscillation. And this, going back to Monday, is a simple example of an oscillation that's driven by the fact that you have sunshine during the day, ionization going on during the day, and less ionization. I always get called out if I say none, because there's other ways other than photons of ionizing. For instance, the particles that are precipitating down. But the elements are recombining during the day, during the night, and therefore the density is going down. The higher you go, the more difficult it is to recombine. And so the rate at which you would go from high to low is, now you're talking about, if you want to think about the driven oscillator example, you're talking about something that is much more of an overdamped oscillator. And it's responding very weakly to that 24-hour cycle, because the recombination time is longer than 24 hours. So it's only varying, it's varying, close to an order of magnitude. All right.
Hey,
So
hey, Dana, we're
yeah.
near a break time.
I know, and I
okay.
just wanted to get to.
Great.
I was just going to leave everyone with the sort of lesson from all of this, and this is just that there are these common elements of physics in heliophysics. This is the propagation of light into, propagation of anything into an atmosphere and then absorption. And the optical depth is critical in all of these. Okay, so I'm going to leave it here. Where I know we did an exercise on limb darkening, as it's called. That's where the stellar atmosphere gives you the same dependence on angle chi. But I think we're going to skip over that and move to the magnetosphere after our break. So everyone, let's take 10 minutes, sorry, get back at the top of the hour. Thank you. Yes, recording in progress. Right. So that was fast introduction to the ionosphere. Now, the whole purpose here, of course, we're aiming at understanding long-term variability. This is to bring you up to the point where you will hear from experts about the long-term variability of the ionosphere. And if you're like me, you'd be like, what's the ionosphere about? So now you kind of know how it comes to be, what the basic physics forming the ionosphere is. So hopefully that will give you a little bit more preparation for understanding why it varies the way it does. And any questions before we move on? I need to do 1 hour to the 50 minutes for the ionosphere, and now 50 minutes for all of the magnetosphere. And the first place I want to start, for those who don't think about these things, is just to talk about the shock, because this is a big part of what we see in the magnetosphere. And if you haven't had an exposure to shocks, it's not too difficult to understand what they are. If you have fluid flowing supersonically, so it's going faster than the speed of sound, and the ones here mean this is upstream of the shock. So it's the stuff before, then it really cannot know anything about you, right? If it's coming at you, if you're put yourself in the reference frame of the Apollo 11 space capsule, the air below can't know there's an Apollo 11 space capsule coming, because you're coming at it, or it's coming at you, if you're in the capsule, faster than the speed of sound. And information travels at the speed of sound. So it's in for a big shock, to pun intended there. And what happens at the shock is the fluid slows down, the fluid slows down, and it gets heated. And here's a nice diagram of the shock that forms around a simulated Apollo 11 re-entering. And you see this is temperature in Kelvin. And so the blue is a nice 200 Kelvin, that's a little chilly, but it's going, you can see this shock, and it's just this wonderful parabolic, or it's actually a hyperbolic shape. And the temperature goes up to, it's 20,000 Kelvin upstream of that. Is that right? Am I doing that right? Yeah, very hot. And so this sort of brings up one, and so the whole point is that the kinetic energy of the incoming flow is partially converted to thermal energy, to temperature. And so the upshot then is that the sound speed has gone way up, the speed of the flow has gone down, and now it is subsonic. And when you have subsonic flow, it's going slower than the speed of sound. It knows about the capsule. It goes around the capsule. Okay, so it's only in this subsonic region, post-shock region, that the flow can actually go around the space capsule. The other thing I like to point out is if you ever see Hollywood representations of this, and there are quite a few, one starring Tom Hanks, and they try to give you an explanation for why the space capsule gets so hot during reentry, and they always appeal to friction of air, which just makes my skin crawl. It's actually a shock, right? What they're really worried about is the temperature generated at the shock, because that's what heats up the air, and the air is what heats up the capsule, and there's no friction involved. But let's move on. Let's move on. This is the same thing that happens in the solar wind. If it hits an object like Venus or Mars, which doesn't have a magnetosphere, that's just like the space capsule. The solar wind is going, say, Mach 8, so much faster than the speed of sound in there. And actually, the magnetic field is fairly weak. So if you look at all the other MHD waves, it's going faster than any of them. And that's why it's always depicted as these perfectly straight lines, because why wouldn't it just be going in a straight line? It doesn't know anything. It's just going out into space. And then you hit the shock, which is the bow shock, and everything I just said happens. The plasma heats up, and it suddenly becomes subsonic, and it says, hey, there's a planet here. Let's go around the planet. Okay, so that's the easy side. The harder side is if you have a magnetic field, then what happens is the magnetic field forms that obstacle, and we'll talk a little bit more. It's not a rigid obstacle like a planet, but nevertheless, it behaves like a nice rigid object. That is, the plasma can't actually penetrate the magnetosphere, so it knows it has to go around it, but it can't know that until it's gone through the bow shock. This is the shock where the plasma has to slow down from supersonic to subsonic. It slows down, and I don't want to go through all of the shock conditions, but I think in one of the activities, you're given the fact that for a monatomic plasma, for a plasma that's made of point particles, the maximum slowdown you can do is a factor of 4. If you are going at Mach 11 million, you are only going to slow down your velocity by a factor of 4 on the downstream side, and the density goes up only by a factor of 4. But what has to happen if you're going, that you'd say, well, if I was going at Mach 8 and I slow down by a factor of 4, I'm going at Mach 2. But that's not true, because the Mach number is based on the sound speed around you. And so it's the heating that has really produced a higher temperature and therefore a higher sound speed. So now, although you're only going a quarter the speed, the sound speed has gone up by much, much more. And now you're subsonic and you flow around the planet, or around the magnetosphere. So this is sort of the simple picture, and more complicated versions of this are, all over the place. And one of the things I will point out is when you talk about shocks, you're really only talking about the component of the velocity normal to the shock, okay? And so the component that's parallel to the shock doesn't have to surprise anything. And so it's the same on both sides of the shock. That's what actually causes the streamlines to bend. Their parallel component stays the same, the tangential component, and the normal component decreases by a factor of 4. But when you get out to the edge of this hyperbola, what's really happening is you get to a phase where the normal component of the flow is no longer Mach 8, but it's actually just Mach 1. And that's boundary, that's at the edge of not being supersonic. And so really the jump you're going to get across a Mach 1 shock is very minor. It's more or less just like a sound wave, a linear wave. So what you can do is work out a simple geometry here. The angle, if you're traveling at some Mach number m infinity, let's call it 8, then what you want is the component normal to the shock to be 1, and you just solve for, you put in the algebra, M is now, M infinity is, sorry, M normal is M infinity sine the Mach number, set that equal to 1, and you get, this is the angle, the Mach angle that you will go to asymptotically. So far away from any of these shocks, let's say out here, you're going to that asymptotic Mach number. And that's because the incoming Mach number is now 1, and you're probably, and you're only going to be going, well, you will be going faster than the speed of sound downstream, right? Because this is just your normal component. The tangential component is the same as it ever was. So this takes us to the activity 65 that I know some of you worked on. I know there was at least one question which I attempted to answer in Slack, but I'm not sure if it was too late for people to see. But I want you to break out and try to figure out what angle, this was the real issue of the question. The question is, there is some point here where if your normal component of your velocity goes down by a factor of 4 and the tangential component doesn't change, that by the time you get to the other side of the shock, you are still supersonic. That is a particular angle, and it's an important angle. So I want to have you break out and just try to work through. And here are from the heliophysics, principles of heliophysics. Here are some of the important equations, but let me see if I can talk you through. One of the things they say is you can ignore beta and you can ignore the pressure of the solar wind. So this is what you get. The temperature downstream is just going to be related to the density upstream, or sorry, the kinetic energy density, or the ram pressure, I should say, upstream. Let's see, do people feel that they're sufficiently lost that they don't want to break out and try to work on this problem, or are some people comfortable enough that they want to break out? Why don't I hear from people who say, well, you know, if I went to a breakout room, I wouldn't know anything about what to do.
So really quick, in the activity, it doesn't mention that the speed changes by a factor of 4.
Let's see.
Something missing that confused us also.
Doesn't it say, isn't this, I think I copied the text. For a wind, V, solar wind, the density cross, is a factor of 4. The density, yes, sorry. So that is implied by the fact that the mass has to be conserved.
Oh.
So yeah, maybe the authors of this textbook should have been helped you out a little bit more. But yeah, when I said that the
Only edition 1.
What?
It's only the first edition.
Okay, all right, good. We'll take note of that, Nick.
Right.
But I'll leave the question out there because there's no point breaking out if everyone's going to be kind of lost. We can go through this as just, you can watch me go through it.
Should we get a thumbs up for?
Yeah. Could you look at the participants? Let's have a thumbs up for everyone who wants to do breakout session and sort of work through some of this to get this angle. That's really what you're after, is this angle. Estimate the direction. The flow is just supersonic.
And do a surprise for anybody who wants Dana to go through it.
Just go through it myself.
Okay, so we're getting mostly surprise faces.
Okay, so let's do this together. So here is the key thing: is you're going to use this expression here, which tells you the downstream temperature and density, and I basically solve for T2, and what I get is I have the solar wind speed over rho 2. That's where the density drop of a factor increase of a factor of 4 is going to happen. So this turns into 1/4. And then V solar wind speed is just V solar wind speed. So you do have to, and then that drops by a factor of 4, and then you square that. So you get to have to do the algebra of 1/4 minus 1/16, and that's where you get 3/16. There's a factor of 2 up there, so 3/32. That's actually given to you. But then this tells you how to convert the temperature, find the temperature from whatever the solar wind speed is. Then you want to find the sound speed downstream, and that's really just 5/3. Well, there's the sound speed. And so you really get to 5/16 of the solar wind sound speed normal to the shock. You put in your factor of 4 again, and you find out it's a factor of 5. The sound speed downstream is a factor of 5 larger than the sound speed, the actual flow velocity. Okay, so your Mach number is actually 1/√5. This is a lesser known result of hypersonic shocks. Your density goes up by a factor of 4, your velocity goes down by a factor of 4. That's kind of common knowledge. The thing that people kind of forget sometimes is your Mach number just goes, no matter what it was before, it goes to 1/√5. Okay. However, that's just normal to the shock. And what you want is for the parallel component, which is the same, the solar wind version and the downstream version is the same. And you want that to be greater than 4/5, or actually equal to 4/5 if you're just at to be sonic. So if you add up the perpendicular and the parallel components, you'll get the sound speed, right? So then you basically find out, oh, I need this thing to be 1/4, the parallel component to be 1/4 of the perpendicular component, and then you take the square root of 1/4 and you get 1/2, and so you know the ratio of those two has to be 1/2. And then that actually, I didn't diagram it here, that gives you the tangent of this angle that you're really interested in. So the tangent of the angle is 1/2. I had to put that into a computer because I don't know arctangent of 1/2. It's 27 degrees. So that's the key here, is that when you're coming in and you're 27 degrees from the normal, your parallel component is going to go down by a factor of 4, and your perpendicular component is going down by a factor of 1/4. Your parallel component is staying the same, and you will basically be Mach 1. So everything north, everything outside of that 27 degree band is all supersonic, even after the shock.
Huh.
The normal component has become subsonic, but there is a region that is actually still supersonic. So it's only this nose region of the shock where you are subsonic, okay? And the temperature increases, as we said it's pretty much converting all of that, almost all of that kinetic energy to thermal energy, although you even compress it even more when you slow down subsonically. You use Bernoulli's principle for that, and you just go to, you increase by a factor by 1/15 more, and that's the temperature you get right at the nose point, the stagnation point at the front. Okay, so based on that, you can actually work out what the temperature is, not knowing the solar wind temperature, but just assuming that your solar wind is 800 kilometers per second. That's a fast solar wind. Go through all similar kinds of arguments here, and what we're going to get, you basically find out that right where you're stagnating, right, you're going to get a temperature we worked that out before, but now we'll turn it into real numbers, and we find out it's 7 million Kelvin. So no matter what the solar wind temperature is, by the time you hit this bow shock and have to slow down and become subsonic, your gas pressure, your gas temperature, your plasma temperature has gone up to almost 8 million Kelvin. So the magnetosphere is a very hot place. That's actually hotter than the solar corona at most places, except in flares. So the solar corona has created a solar wind, and the solar wind has accelerated as it's gone out and then been stopped. Does that strike anyone as odd that, you know, by the time you get to the Earth and you basically reconvert all of the kinetic energy that you got to create a wind, that you're now hotter than the corona was to start with? Does that strike anyone as odd? This is part of the thing that we're not covering in this summer school. It's the solar wind. No one's surprised. This, I would offer, is a real solid evidence that there is energy being added to the solar wind a long ways out. It's not just a hot plasma that's expanded into space adiabatically. And by adiabatically, I mean without heating. It has been heated continuously, or not necessarily continuously. That's what Parker Solar Probe is out there to tell us. But for some region of that initial journey, it has had energy added to it, a lot of energy. And so by the time you stop it and try to recover all that energy, you're at a much higher temperature than you started with. Okay, so this is the sort of story of what's known as the bow shock, the place where the solar wind has been slowed down outside of the Earth's magnetosphere. And this is sort of a big picture of that. This is the magnetic field that the Earth has generated. We talked about why the Earth has a magnetic field. And the solar wind has to go around that, so we get this bow shock region. But the next thing to think about is the solar wind. The obstacle here is actually not a solid body like an Apollo space capsule or a unmagnetized planet like Venus. It's actually a magnetic field. So it's kind of squishy. And the solar wind is going to squish it. However, by the time this happens, it seems to have reached an equilibrium, and that's known as the standoff distance. And those of you who've worked in the magnetosphere have sort of worked out this, but after all of that, we have a plasma pressure right at the nose that is really the ram pressure of the solar wind converted to plasma pressure. And the squishiness says if the magnetic field pressure on the other side of this obstacle were smaller, then the high pressure would push it in. If it were too large, it would push it out. So the equilibrium occurs where that magnetic pressure balances the solar wind pressure. And the solar wind pressure, we basically take the ram pressure, and then this 4/5 comes out from doing all that math we just did. 4/5 of the ram pressure is what the stagnation pressure at the tip is going to be. That has to equal b squared over 8 pi. That tells us the magnetic pressure that has to balance it. What we do next is, sorry, this is different chi. This is not the angle. This is the magnetic potential. So we're basically saying, oh, let's assume this inner magnetic field is current free. So it's essentially a dipole, or this is a little bit better than assuming a dipole. The dipole is the first term, and the second term here is to account for the fact that there's current there. And at any rate, what you have to do is figure out what the magnetic field strength is. That's the gradient of the potential in the theta direction. You work it all out, and you basically, oh, I should point out the most important thing is this is what would stand in for the dipole moment. I didn't want to go in for a dipole moment. So it's basically whatever the magnetic field strength is at Earth times the radius of Earth, and then you divide it by the radius you're looking for squared. So that's basically the magnetic field is falling off as 1 over r cubed. Long story short, but this basically gives you, when you've done it, There's a dipole. There's an image. This gives you the Chapman-Ferraro distance. Same guy, very, very important in this field. Tells you that the distance from the Earth to this boundary that the solar wind is going around, the magnetopause boundary, is goes as the 1/6 root of the ram pressure of the solar wind. Okay, 1/6 root of the solar wind ram pressure. So that's really, you know, I put in some math here because I want to be honest about it, but really what we're saying is the magnetic field is falling off as 1/r³. The magnetic pressure is falling off as 1/r⁶. And that magnetic pressure has to balance the solar wind pressure. So voila, the ram distance is the 1/6 inverse 1/6 power of that. It also depends on the strength of your magnetic field. I put that in for good measure. And really it all scales with the radius of the planet, right? If I had the same magnetic field strength, but my planet was twice as big, then the standoff distance would be twice as big. Okay, so this is the front side of the magnetosphere, at least in simple pictures. And so if we put in some numbers here, you can see if I say that the Earth's magnetic field is 0.3 Gauss, and I put in some simple numbers for a slow solar wind. So a solar wind velocity, a slow solar wind is 400 kilometers per second. There's the mass density of the solar wind. I'm going to keep that the same in both cases. And you just plug in all those numbers, you get 11.7 Earth radii, right? This whole mess just turns into 11 because I told you what the magnetic field strength of the Earth is. That's really the dipole that goes into the dipole moment. And then the ram pressure, I take the 1/6 power, and so it's 11 solar radii out, or 12 solar radii out. If I double the speed, right? But remember, that's really going into, I square it and then take the 6th root. So it's a 1/3 power. So I'm really going to decrease the distance by 1/2 to the 1/3 power. So it doesn't change that much. It only goes to 9 solar radii, or Earth radii. So there's your standard. That's how big the magnetosphere is on the sunward side. It's basically somewhere between 12 and 9 Earth radii. Any questions? I know that was a lot to take in, but it sort of gives you an idea of how this, at least the day side of the magnetosphere, is structured. You have this region where the solar wind is being slowed down, and that's where it's getting its pressure from the shock, the bow shock. And then you have this magnetopause where it separates the solar wind from the magnetic field of the sun, of the Earth. And that magnetic field is providing the pressure to stop the solar wind. And the faster the solar wind is coming, the smaller that bow shock, that magnetopause is good, the closer it will be. Okay. So just, this is one of the activities. And one of the things it wants you to do, and this is more relevant for studying storms and things, if the solar wind speed went up to 2,500 kilometers per second, right? This is just an example of what could happen. And that has actually happened when we have these storms, CMEs and things like that. You plug it in, you find out it's, where did I put it down here? Oops. Oh, all right. I think it's beyond here. Yeah. Yeah. Sorry. So I don't have the answer here, but oh yeah. There it is. You end up going closer than geosynchronous orbit. That is 6 solar radii. That's where the satellites exist. And you work out that just using Kepler's law. And so you're going to get a magnetopause that comes inside of the solar wind, inside of geosynchronous orbit for these big storms. Okay, so and just to talk about some other planets, the magnetosphere of Jupiter works exactly the same way. So you have a big magnetic field, and it's actually 15 times the strength of the Earth at the surface. However, it's a bigger planet. Now the question is how the speed of the solar wind has changed and how the density has changed. And then we plug it into that. What you find is that the solar wind speed doesn't change very much. It's supersonic, nothing can really slow it down until it hits a planet. But the density falls off as distance squared to conserve mass. So the ram pressure of the solar wind at Jupiter is much smaller, and therefore the magnetosphere is much bigger. And what we get is it's 50 Jovian radii, which you can see is almost is bigger than the sun, right? So the Jovian magnetosphere is actually bigger than the sun by a factor of 5. It's sometimes the biggest thing, called the biggest thing in the solar system. Okay, and so here are some of the well, this is discussing other planets around other stars. So this sort of is everything I wanted to give you as a primer on that side of the magnetosphere. Now, some of the other things we're going to talk about are related to the magnetotail, the part of the magnetosphere on the night side. So we've already talked about, we have a solar wind that comes in, it hits the bow shock, and then it hits the magnetopause and goes around, and it's heading out into space on the backside, but it's actually creating this stretched out magnetotail. And the other thing that we have to acknowledge is not all of the magnetic field from the Earth is closed in this way. It's not all participating in the deflection of the solar wind. And so there is a region that is open. And what's happening at the magnetopause is magnetic field lines from the sun, if they're oriented correctly, southward, are going to reconnect with magnetic field lines from the Earth. And basically you'll see in this wonderful cartoon that they will then form these open field lines that go from the interplanetary space into the North Pole. Okay, so there's a boundary between field lines that are connected from the south to the north in the Earth, and those that are connected from space to the north in Earth. Okay, that is the auroral oval. And this field is continuously reconnected on the day side to form open field. And to get a steady state, we need to reconnect it back. And so we need the magnetic field that's the same amount of magnetic flux that's opened up at the day side to be closed back down in the magnetotail. And this gives us a rate at which magnetic flux is being opened, and then the rate at which it's being closed, and those two have to balance. Okay, and so what happens is the field gets stretched out. You have this large neutral sheet, which is just a way of saying that the magnetic field, it reverses from going away from the Earth towards the Earth. Okay, and here's a sort of theorist cartoon picture of that. In the south, it's going away from the Earth. And in the north, it's coming up from the Earth. And this is sort of a classic picture of a current sheet. You've got field below going one way, field above going the other way. And so the blue are just using your right-hand rule to form what's the current produced by this kind of magnetic structure. And that is what's known as the neutral sheet. And it's a current that goes, well, towards you in this diagram. And that's always there because the magnetic field is being stretched out by the now it's supersonic again, but that post-shock portion of the magnetic field. Okay, now the last bit of trying to understand this, no, not the last bit, the next bit of trying to understand this is there's some amount of magnetic flux that was always open. Okay, we've balanced the reconnection at the day side with the reconnection at the night side, and that basically is a region that is open, and it's going to stay the same size. There's no way of really figuring that out ab initio, but once you have that flux, the total amount of flux that's in that, you can work out how wide this magnetopause is. And assume that it's much longer than it is wide, then it really looks like a cylinder. And it's a cylinder that has some amount of open flux. And this is sort of a picture of some of these that are taken from some of the volumes. Even Saturn has this same structure. So you see nice aurora at the open closed boundary of Saturn. Enceladus, oh, sorry, that enters into all of this, but and there's Neptune. And then, so that boundary is what maps down to this region that we call the auroral oval. And I think we will talk about some variations in things that go on there. But what I want to get to is how big is this magnetotail? And here we're just going to assume that the flux in the magnetotail is exactly the same as the flux you get in this polar cap. Okay, so all of this stuff that's in here, pretty much covering Greenland, covering the Arctic, bits of northern Canada, and almost none of Alaska. But all of that magnetic field, so that is the North Polar magnetic field, which we said is 1/3 of a Gauss, the angle of that polar cap, and then pi r², right? So that's going to give us 10 to the 17 Gauss centimeters squared, or Maxwell's. That is the total amount of flux that's open at the North Pole. And we're going to assume that same amount of flux is present, well, in the upper half of this lobe, and figure out how big the magnetotail has to be. So the question is, how strong is the magnetic field there? And we're going to once again go back and say, well, the magnetic pressure there, 1/8 pi b², has to balance whatever the magnetic, has to balance the pressure of the solar wind, right? And here, there really hasn't been much of a shock, right? This has gone through at that thing where the Mach number is close to 1. So it's pretty much the same magnetic solar wind pressure as we've had before. And that has to balance this magnetic pressure that's in the magnetotail. Oops. Oh, shoot. Right. So we just plug in the numbers there, and we find that we get about 25 solar radii. So this is bigger than the magnetopause, but not that much bigger. We've got this 25 Earth, I keep saying solar radii, Earth radius tail that goes downstream of the Earth. And that is the magnetotail. It's just this big bundle of open field lines that's been swept downstream by the solar wind. Okay, I'll give you some pictures of other auroral ovals. There's one on Jupiter. There's the nice photogenic one on Saturn. Any questions so far? I know this is going fast, but.
Hey, Dana, I think you has a question, but I can't parse the question.
Okay.
So maybe you can just speak up. Yuhang? Oh.
Let's see if I can.
Hello. Hello.
Yeah.
The what determines the position of reconnection at the magnetotail. So there is some reconnection at the near Earth boundaries when it is also favorable for the substorm and all. So what determines the position of the reconnection at the magnetotail?
That's a good question. That really has to do with conditions for reconnection. In this picture, I basically said this thing could go downstream forever, and it creates this nice current sheet. The question is, how long would magnetic field adjacent to a current sheet last that long? And so, as I understand it, when I see the literature, there is a lot of discussion about what conditions have to occur in a current sheet to start reconnection. Actually, I think Amitava has written many papers on that. I think one of the things that happens is if the current sheet gets thinner and thinner, and here it's just drawn as a sort of cartoon, if it gets thinner and thinner, it will ultimately cause reconnection. The current density would go up if it got thinner and thinner. And if there were any kind of resistivity, which there's not, you get a stronger and stronger electric field from that. But I don't know if Amitava has any insight into what we should tell people is the reason that we get reconnection where we do, at some X line or some point along the current sheet. Or maybe Amitava is.
Okay, thank you. Thank you.
Okay, sorry. So maybe in office hours or something, if Amitava is back with us, he can tell you more details about what that might be. But I'll just say it's still a big open question, and the magnetic reconnection can occur in all sorts of places, and it chooses to do it usually in sort of places far downstream. Okay. No, one of the last things I want to do. So one of the things that our last lecture told us was we have this magnetic field from the Earth, and that's really moving very slowly. We had like 10 to the minus 4 meters per second or something is the speed with which the molten core is moving. And if you think of magnetic field lines as frozen to that, and Amitava gave you sort of a run through of how MHD talks about field lines being frozen. If the field lines are frozen to that, how can they move across the North Pole or region of the magnetosphere as fast as they do, right? So what gives? We have very slow motion where the magnetic field is generated and very fast motion out there. Okay, but the thing is that between those two regions where field lines are frozen to the material, to the plasma or the molten core, there is a solid crust, there's an atmosphere, there's stuff that are not conductors, they're insulators. Okay, and at that point, there is no concept of frozen in field. So you have frozen in field deep in the Earth's interior, and you have frozen in field in the magnetosphere, but there's a layer where it's not frozen, and therefore you can actually have those two different speeds meeting each other. And here's a sort of picture of what I mean by that. You have the atmosphere, and the magnetic field is, let's just say, stationary, right? 10 to the minus 4 meters per second is essentially standing still. So the magnetic field lines in the atmosphere are just going to be straight down, and they're going to be not moving at all. And then you have the solar wind, which is moving the magnetic field at some speed that comes from the solar wind in the magnetotail, for instance, or sorry, in the polar regions, shall we say. And what happens then is, if you imagine this happening all at once, you will basically take the solar wind magnetic field and bend it, because you're trying to move it to the right, and it's attached to field lines that are straight. So you'll get a current. You have an electric field that's minus V cross B, and that's the velocity of the field lines. And as you move down, you eventually get a point where you get a steady state, sort of. The field lines in the magnetosphere are moving at the speed that they have to move at, and the magnetic field in the atmosphere is stationary because it has to be stationary. And this is the layer where those two get matched up. And there is there's an electric field that has to exist there, and it is sustained by some amount of conductivity, sigma. Okay, and that is a crucial aspect of the ionosphere itself, is that it sustains that, it has that conductivity, and therefore allows the magnetic field lines to slip, if you will, past. The ones at the bottom are stationary, the ones at the top are moving, and the ionosphere is the place where those things are stationary. If your motion was only in a slab, you would actually get, and here what I've done is turned everything around. So instead of the electric field coming out at me, I have it go to the right. And I'm saying, okay, only a certain region in the polar region is moving, and in this case, it's moving away from me. So sorry about this, but we have two different views of this. One, the solar wind is moving to the right, and then I turn 90 degrees to look at it from behind, and the solar wind is moving away from me. And the current in the ionosphere is moving towards me in this view. Here it's moving to the right. And the electric field is always to the right, but the electric field only turns into a current in the ionosphere. And on the outside, I basically have the situation where the magnetic field isn't moving on either place. It's just basically stationary, both in the atmosphere and the solar wind. So nothing needs to happen. And so what you have to do is you have this boundary between places where the magnetic field is coming out at you and places where it's not, it's just going straight down. And that gives you current. Use your right-hand rule and you'll get current going down. And over here, you get current coming up. So this is a slab version of that. And you see that you have this current that basically comes down out of the magnetosphere, through the ionosphere, and back up into the magnetosphere. This is a current system that you get just from trying to move plasma just in the open region, because that's the only place that you have to move it. The rest of it, the magnetic field of the Earth is screening out the solar wind, and so there's no solar wind there. There's nothing to move these things. Okay, and that little diagram gives us the idea of a current system that flows in the Earth. And this is the sort of picture, I think it comes out of, let's see, comes out of one of the chapters, and I forgot to note it here, of everything I've just talked about. But just looking at the North Polar Cap, and they've given you nice little numbers here, which is the fate of the magnetic field line. It's going 1, 2, 3, 4, and then it zooms around at the edge. That's the slab here. And that's basically the way that the magnetic field motion has to go. And it basically tells us that there's an electric field that crosses from A to B. And if I integrate that electric field, it is really telling me how much flux is coming in on one side, phi dot on the day side, how much reconnection is going on there, and how much reconnection then has to go on at the magnetotail. Remember, we assumed that those things balanced. And then to get from one place to another, you have to move the magnetic fields in the way I just said. That creates an electric field in the way I just said. Right, here's the electric field. The electric field goes from one side to the other, across the cap. It's a cross cap electric field. And if you integrate the cross cap electric field, you get the cross cap potential, cross polar cap potential, I guess I should say. That is the measure of how much reconnection is going on, because it's basically allowing us to see the magnetic field lines being dragged across the ionosphere, which is allowing them to move relative to the rest of the Earth's magnetic field. Here's another picture. Again, this one I think comes from volume 1. I draw cartoons that are just as crude looking, but mine maybe not as informative. But this really shows you that whole picture. This is the velocity far up, the velocity of those field lines that are in the solar wind, frozen in part, and how they circle back. There's the current system I was pointing out. So the current comes down, goes across, and then back up. The electric field is what drives that current through the ionosphere. And that is the field-aligned currents. This is the sort of structure of the place where the ionosphere and the magnetosphere meet. And if you get a cross field potential, I copied this from somewhere, 50 kilovolts, that gives you the rate at which these magnetic field lines are being reconnected. And if you take the number we already calculated for how much flux is in the open region, this tells you that the whole process is going to take about 5 hours to reconnect at the day side, move to the night side, and then reconnect again. Okay, that's just taking the potential phi dot and putting it in the denominator below phi, and that gives you the recycling time. So that's exactly 10 minutes of the hour. I know that was a lot, but I was attempted to show you that the ionosphere is basically just a product of EUV and X-rays from the sun's transition region and corona, the parts that emit those short wavelengths. It's going to, therefore, the ionosphere is going to get smaller at night when there's no photons, and it's going to get smaller in the solar minimum when the corona and the transition region are less bright. And then also that the solar wind is deflected by, deflected by the magnetosphere. That's what we're really going to care about. And that the magnetotail is just a product of this magnetic reconnection. And that's everything for this. I think next we get some office hours. Is that right? So I will stop sharing now and take any questions, and then we can have the questions move into the office hour.
And before people jump off, I have a quick announcement.
Okay. I don't hear any questions now, so we're going to maybe have some questions during office hours. Nick, your announcement.
Oh, okay, great. Well, you got a super cool talk from Jesse, so just
well, thank you very much.
Yeah, so Saturday, so 2 days from now, we have this participant presentations or participant poster session that we are have planned. And so we've got a number of people already have submitted posters. You can preview posters on the link that is on the primary schedule, which I think you all have. And also we are, so as part of this, we're going to start off with a series of e-lightning talks, right? About 2 minutes for you to advertise. Catherine's put the link in the chat, so it's also, I think, it will be on Slack. We'll start off with some e-lightning talks for you to advertise your poster. It'll be just an advertisement for a poster, so it's an elevator pitch type thing but specifically for your poster. And then we'll go into 2 sort of tracks of poster sessions. So what I've tried to do is mix the posters up by topic so that we've got in each track we've got some of each topic, but solar and then geospace and atmospheric and solar wind, or aeronomy and solar wind. So there'll be some of those in each track. So there's a chance.
Surviving.
Okay, well it's better than the alternative.
Yeah, although sometimes it feels like not surviving.
Yeah, I know. I know the feeling. Okay, well then, I guess I will introduce our speaker who's going to talk about forecasting, and that is Dr. Scott McIntosh, who used to be, you don't know, but we used to have this summer school in the center green facility of the High Altitude Observatory in Boulder. And Scott was the director of that observatory for many years until he decided to move up the ladder. And now he is deputy director, is that right, of all of the National Center for Atmospheric Research, NCAR, which is the organization that includes as one of its many parts the HAO. But I know Scott since, boy, I think you were a postdoc working on the on SOHO at the time, and that's a spacecraft.
Knee high to a grasshopper.
Yeah, well, we were both young back then. Anyway, so I'll just let you take it away. I will monitor the chat in case there are any questions for you from the chat. Otherwise, yeah, take it away, and we'll go until well, we're sort of 5 minutes late, but so we'll go till about 5 minutes of 11 or ish, whenever it makes sense to break, and then we'll take a 10-minute break, and then you can pick up after that.
Yeah, thanks, Dana. I've got a natural break in the presentation. Let's hope I can get there. So, thanks to Dana, Amitava, and the others, Nick, for inviting me to give this presentation to you all. I hope it will be entertaining and informative, although I can guarantee neither. I think one of the things I'm going to share with you something that I've learned in recent times, and have really learned by accident, actually, unfortunately, that, and I'm going to try and walk you through the bizarre world that is solar cycle prediction. But in doing that, we're going to realize that there's actually a thread that illustrates how science develops and kind of over what timescales that it develops. So, and then I'm going to close with a bit of a neat result that's not even published yet. So I know that this has been recorded, so I'll warn anyone not to share that when I get there, but let's hope I do get there. So I'm going to open the first slide on here has 3 dead guys. Most of solar physics involves dead guys. And they are, from left to right, David Hilbert, who's famous for time series analysis and a host of other things. Charles Tree in the middle, who was the director of the Kew Observatory in London. He's famous for things that are used widely in meteorology, believe it or not, more so than astronomy and solar physics. And then the guy on the right is George Ellery Hale. And I don't know if you've seen a picture of him yet, but he's basically the godfather of solar physics. So these guys are going to pop up in various places throughout the presentation I'm going to give. And I will talk a little bit about their contributions or the realizations that they made. So I'm sure over the first couple of days of the summer school, you've met these objects, sunspots. And we're doing a little bit of a chronology, but these are a series of sketches that were composed by Galileo in the 1600s at the dawn of the use of the telescope. And it's pretty fascinating, the amount of detail that Galileo had before he lost his eyesight, but in that wonderful, precious time that he had sequestered to do his science and stay away from politics and the church. I also think you've seen this over the course of the week, but not all sunspots as you document them over time, wax and wane in number. And this is a pretty infamous plot that illustrates that the solar cycle, or the number of spots on the solar disks, has a period, an average period of about 11 years. Excuse me a second. You guys need to leave. Go. I've been interrupted. Yeah. Logan. And those variations continue except when there are no spots. And one of the biggest questions in solar physics really surrounds why there are sequential minima and maxima in the patterns of sunspots. I'm not going to get into that today, but as a puzzle, it's intrinsically tied to the production of sunspots itself. So, and I believe that both Dana and Amitava have talked to you yesterday about dynamo processes and the processes by which sunspots are thought to form, or stellar activity as well. And so the challenge is to understand the underlying physics well enough to project what that system's going to do in the future. Because if you remember, the topics of this presentation is solar cycle or sunspot prediction. So you need to take this piece of information and extrapolate a whole bunch of physics that you can play out in time and in your head or in a computer to replicate the variance that we observe. That's a considerable challenge. However, if you take more information, and Maunder in 1904 discovered that if he plotted the spatial distribution of sunspots, they formed what looks like butterflies' wings when you stand them on their side. And what you see are these progressions that go from mid-solar latitudes, or approximately mid-solar latitudes, towards the equator over that period of about 11 years before they disappear, only to restart again at mid-latitudes. So that's now two pieces of information you have. You have the total number of sunspots on the disk, and you have the distribution of sunspots with latitude. Subsequently, just 15 or so years after Maunder, Hale discovered through the novel use of quantum mechanics that was just new at the time that sunspots are magnetic objects. And following years of study, he discovered that they not only were they magnetic objects, but the polarities of the spots as they follow the butterfly diagram flipped and went through a complete oscillation approximately every 22 years. And this has now become Hale's law, or the Hale's law of magnetic polarity. And so the butterfly is not just a butterfly, it's a magnetic butterfly. And so now you have an additional or more information to help you solve that challenge puzzle. And just to illustrate what that looks like, I'm guessing that you've probably seen this animation, but this is basically how you would construct a butterfly diagram that then illustrates how these things work and how the system works with time. You'll see solar activity maxima through minima and back into maxima again. I'm going to let this play out. You guys need to go.
Where's the slipping slide? The greens are coming over. The slipping slide is out.
Hold on a second, Dana.
All right. Yeah. So, any reactions so far? We've seen this. Okay, Scott. Okay.
To my kids.
Yeah.
Ignorant little buggers.
No. Yeah. Okay, good.
Anyway, so continuing the slow march. Not only sunspots, the sunspot number is actually different in each hemisphere of the sun, because I'm not sure anyone that would expect it to be completely hemispherically symmetric. This leads to more often not, sunspot cycles that are double peaked. So when you look through the time history, and this is just one example, that the sunspot oscillation or the sunspot cycle has multiple peaks, and often that's associated with the fact that the two variances in each hemisphere are slightly out of phase. More information. So there's another piece of information. So now we're kind of creeping up through the 50s and into more recent times, where we've now started to realize that the sun also exhibits periods of enhanced spot formation. So on top of the decadal scale sunspot cycle, there are large oscillations or large variations in the amount of spots that are formed. And you can see that in this figure here, where the black curve is the total sunspot number, and red and blue are the hemispheres, which I told you are not in phase with one another. But you also get to see now that there are fairly significant surges of sunspot formation in the sun over the course of about 11 months. So, which is not a tidal phenomena, but we think is a strongly rotational phenomena, similar to that forms the weather systems or modifies the weather systems on our planet and other planets. Won't get into that in this presentation, but it's pretty interesting when it comes to things like space weather, because if you think about if a sunspot forms on those periods, then likely so do disturbances arising that arise in sunspots. And so we've started to explore the predictability of these kinds of oscillations. And so just to recap and think a little bit more with question marks, there's 400 plus years of sunspot numbers, 100 plus years of magnetic data. There's a potentially infinite potential solutions to the puzzle of understanding the sun's internal workings because we can't directly observe. And it leads to, well, this is a bit of exaggeration, but many, many predictions of what the upcoming sunspot cycle is going to look like based on that prior information. So before I go on, are there any other questions? No, all fairly straightforward. All right, so here's a warning for you. Niels Bohr is famously quoted as saying, prediction is very difficult, especially about the future. You may want to keep a note of that when someone asks you to predict what's going to happen tomorrow. A famous baseball player also said the same thing, slightly different tone. Another warning comes from my old PhD supervisor. My PhD was in inverse problems and dealing with what we call ill-posed problems, which are a situation where you have lots of data and you have to back out from the data to the physics, the problem being that the intrinsic noise in the problem or the intrinsic variability in the problem doesn't always give you a unique solution. So you basically have lots of possible solutions that match your observations. So I'm kind of dropping a hint here as to what we're going to see as we walk through sunspot cycle forecasting. So first, we're going to look at sunspot cycle 23, because that's really when the prediction game show started. And it was a fantastic ex-colleague of mine. I've met her a couple of times, Joanne Jocelyn, who was the first to publish a consensus opinion on what a sunspot cycle was going to look like. They received, they put out an advertisement in the community newsletter and they received 28 forecasts back. And they really came from a bunch of different types of methodologies. So I'm going to try and explain what these are. The empirical ones are largely numerology. So it's people playing with, just playing with numbers and realize you're playing off of the 11-year solar cycle and saying, well, that's just going to carry on again. We have climatology forecasts, which are basically, well, the sun's just going to repeat what it's done over the past 3, 4, 5 sunspot cycles. So I'm going to use that and bootstrap it to the end. The recent climatology type models were just using the last couple of cycles. Neural networks is an interesting one because in '97, neural networks were a kind of new thing and they have a new name, but they're an old concept. And we'll hear more about neural nets in a little bit. And then there's the old spectral methods, and spectral methods are basically playing with Fourier transforms and using the Fourier decomposition of the sunspot cycle, which isn't actually a great thing to do, to project it out forward in time to estimate how the various envelopes are going to align. The last, and the reason I've left it last, is these things called the precursor methods. And the precursor methods are hinting at a lot of research that was done in the late 80s and early 90s, and maybe even before that, indicating that the sun was giving away telltale signs of what the upcoming cycle was going to look like as many as 6 or 7 years ahead of time. And just one of those examples is kind of shown in the chart in the bottom, where it shows the sunspot number in dark black versus the annual the annual auroral index. So the amount of aurorae over the coming year, and what they noticed basically, and I'll show this in a couple of slides, was that the auroral index at times of sunspot minimum was actually a pretty good indicator of what was going to come in the future, which is kind of amazing, because if you think about if sunspot cycles are distinct from one another, that's telling you something pretty cool. It's telling you that your assumption that sunspot cycles are distinct from each other is false. That there is an underlying behavior going on in the sun that carries that information for a good 5 or 6 years before the sunspots appear. Carry that with you a little bit. I've also highlighted 2 sections from the proposal here. One is this idea of extended cycles. So again, that's idea that it's not, that there's more to it than sunspots. And the second, that the polar magnetic field is important. So the sun's polar magnetic field is somehow tied to what comes next. We'll see that in a thread. So Joanne Jocelyn's consensus forecast, because we all know that science is done by consensus, looks a little bit like this. So this is lifted straight from the paper. If you want to read it, it's in should be in the reading materials. But it came up with a mean sunspot number of around 130 or so. And just for giggles, since we are now 20 plus years past the time, we can compare to what actually happened. So as you can see, actually not a bad job in terms of the amplitude of the cycle, but I would argue that the timing was quite a bit off, probably by a couple of years. And one of the things you'll also know here is that sunspot cycles, like us, are not symmetric, right? So they're also not sinusoidal in origin. So they have a sharp, almost linear rise phase and what looks like an exponential decay from the peak. So one of the things that's at the end of Joanne Jocelyn's work was advocacy that prediction research should be supported, and it should still be supported, along with synoptic scale measurements of our star, so that we can understand how these pieces of information work together. And the advocacy here was that they want to build a physical rather than empirical basis for the production models, right? So a lot of what you've seen in that earliest endeavor were empirical relationships that had been derived for basically 100 years. The most interesting of the precursors is a real credit to someone called Joan Feynman. She had a pretty famous brother, but she was famous in her own right. And this is back to this idea of the auroral indices and the geomagnetic indices. And if you look at the open triangles and the closed triangles in this plot, you can see that the upper set of curves, so the geomagnetic indices, seem to lead the behavior of the sunspot pattern, so the envelope, by a good couple of years. It doesn't just do it once. It doesn't do it by random twice or 3 times. It seems to follow that same pattern for 140 years. So there's maybe something to that. So that's a real credit to Joan and some other colleagues at the time in the late 70s and early 80s, but largely that work has kind of disappeared. Just to illustrate how good the correlation is between the geomagnetic indices and the sunspot numbers. So bearing in mind, these are about 5 years apart, it's pretty strong. So I'm going to hold in reserve that why this might be so good. So just recall this idea of why is the sun carrying information or giving you a telltale sign about something that's coming 5 years later. Into sunspot cycle 24. So now we're getting a wee bit more sophisticated. And Joanne Jocelyn's advocacy actually led to a systematic program at NASA and other funding agencies for dynamo research. So this physically motivated basis for studying the sun and sunspots and their evolution. And if you want to read the paper in detail, it's in your reading materials, but Dean Pesnell put together a kind of compendium of 50 forecasts that were put forth for cycle 24. So it's our same methodologies, the precursor, the empirical numerology, climatology, recent climatology, neural networks, spectral methods, and now these newfangled dynamo models. And they were all ranked based on their approximate, the amplitude of the sunspot cycles. So they were not really focused on timing, more the amplitude. And the mean of the distribution is about 115 and plus or minus 40. So somewhat a little bit smaller than cycle 23. And we'll see how well they did. But the prediction panel split into two camps. One camp that thought it was going to be very strong and very quick rise, and another group that thought it was going to be a late, low rise. So the groups of models were basically decoupled. One was the numerology group, so the early one, and the other was the physical models group. And so if I compare now with the benefit of hindsight to what actually happened, amplitude is somewhere between the two, and it looks like the timing was off again. But I'm not sure, having not dug into the models in any great detail, I can't tell you what they did about the timing, but I would argue that there's something awry with the physics at this point still. And now we come into another piece, which is actually pretty important. So one of the most accurate of those forecasts actually started to look at the evolution of the sun's polar magnetic fields. And it's pretty interesting because it's very tricky to measure the sun's polar magnetic fields. And one observatory on the ground has been measuring them steadily since 1974. And actually it provided one of the most accurate things. So we've seen a progression with Joanne Jocelyn's work where it was an emphasis, we need more physical models. And now that the physical models are starting to come through, the physical models are now starting to point to polar magnetic fields as being key. Okay, so that's cycle 24. So this is really the rise of the physical model, and this has been plundered from Andres and Debiandu and Pete Martins and others, just illustrating what one of their polar infused dynamo models looks like. I don't know if Dana was involved in the creation of this thing, but really pretty spectacular looking movie. And it shows basically how, at least in this realization, how the magnetic fields ingested into the polar cap are twisted and torqued by differential rotation before erupting and spitting it out to produce sunspots. So it's really quite a beautiful movie. Whether it's truly representative of the physics or not, I'm not going to say a thing, but it is pretty nice. And then we get on to cycle 25, because right now cycle 25 for some reason is causing a bit of a stir. And I think maybe this is because I'm not old enough and long enough in the tooth, but maybe it's like this at the start of every solar cycle that everybody speculates wildly for about 2 years before the people that were profoundly wrong shut up and go away. And so Debiandu Nandi has now compiled a paper, and this paper just came out and just came out in the literature, and it's compiling about 80 or more forecasts. So you can see that the number of players in the dynamo, or the number of players in the sunspot prediction lottery, is increasing with time. And it's our same favorite models, and of course now you'll see that neural networks has been accompanied by what is now known as machine learning, and it's pretty much the same framework except using bigger, fancier machines. But now the dynamo models have kind of split into 3 different categories. So if any of you have seen The Life of Brian, maybe you'll understand what's going on there. So it's split into assimilative polar field models, like the one I just demonstrated, surface flux transport models, And then the big kahuna, and that's evolving most rapidly, I guess, are the full comprehensive magnetohydrodynamic dynamo models. I don't know if Dana or Amitava covered those, but there's really kind of 3 different flavors, and they take their roots from observations back in the late 1950s by Babcock and Babcock that described the motion of spots, the decay of spots that were then picked up by Bob later in the 60s, and then codified with some simplifications to make them run on computers. And really our dynamo models, other than the full MHD ones, haven't really, I'll be heretical and say haven't really pushed on much since then. But DiBiendo did the same ranking of the many predictions, and you can see that they're all over the board. Again, the range goes all the way from 50 to 220, and the mean again is about 115. So again, this would be another solar cycle, and actually what you'll be seeing is a slowly decaying set of cycles from 23 to 24 to 25. And there was such an interesting discussion within the panel that they didn't want to actually put a curve on it. They just made it blurry, right? That it's kind of this amorphous blob of models lead to this shaded structure that I'm trying to use my cursor for, with anticipated maxima somewhere in the region of 2025 and a start date in 2020. Just to show it in context, that's what cycle 25 is predicted to look like. And then we're caught up. We're up to date. I've got, let's see what time it is. I've got about 5 minutes before the break.
5 minutes.
Right?
Yep.
But I'm going to show you something that might just stir the pot a little bit, just to queue up for the second hour. And so work that I started when Dana probably met me back in the days of yore, at the behest of my supervisor at the time, was to go and catalog these tiny little bright features in the sun's corona. And just like all things in solar physics, we're incredibly creative with what we call them. And these are called bright points, because guess what? There are bright points in the corona. They're about a few tens of megameters across. They're basically little active regions. But my old boss, Joe Gurman, told me to go and catalog them, capture them, and track them out with time and see what I came up with. Well, when you do some kind of preliminary analysis of these things, you see that if I look at the top of these 3 plots, they're anti-correlated in number with the sunspot cycle. So there's actually more of them at solar minimum than solar maximum. That was already known in the Skylab days. Okay, it's a fairly large discrepancy. They migrate almost linearly from high latitudes to the equator. There's significant overlap in these bands of things, so that those ovals are about 6 years long. So there's an extended overlap between whatever these small features are riding on. And then there's some of this other stuff that I talked a little bit about earlier, that the quasi-periodic in nature. So the number oscillates within about an 11-month period. What are these things? So if you're like me, I'm a pretty curious guy. I went and started to look. And what I basically identified was that not every magnetic dipole on the sun produced one of these regions. So if you look at the HMI magnetogram on the left side, and you look at the corona on the right side, and you can see all the bright points that were identified by my code. But not every piece of black and white in that magnetogram has a bright point associated with it, which is kind of curious. And then I looked at the spatial pattern, and I won't get into how this is derived from the magnetogram, and found that there was a prevalent scale in which these things formed. It wasn't, the scale of a granule down at the megameter range. It wasn't the scale, the convective scale of supergranules at the tens of megameters range, but it was somewhere in between those inactive regions. So somewhere in the region of 150 megameters. So these things are roughly separated by the scale of these mysterious objects that have been speculated to exist in the sun called giant convective cells. And these slides are a real flashback. You'll see where they end in 2012. I pulled them from a very old presentation. And so if you look at these bands and I start to extrapolate out the same spatial scale in the magnetic data, I start to see a weird pattern. Okay, so first is my bright points that I showed before, and you can see them going through a transition from one cycle into the next cycle. You can see significant overlap. And if you can train your eyes well enough to look at the magnetic scale plot, you can see that there's a similar overlap in that beastie too. Actually, where it's strongly magnetic, it's dark. And in the quiet sun, you can see these bands that migrate in from high latitudes towards the equator. If you combine the two by fitting histograms, you get an object that looks like this. This is truly bizarre. Okay, so now I have, at some points in time, I have 4 overlapping magnetic systems present on the disk. Now, if I was just looking at sunspots, I'd think I've only had 2. But there's really 4. Sometimes there's only 2, but most of the time there's 4. And really what we're looking at here is the same cycle that George Ellery Hale discovered almost 100 years ago now. So it's basically the Hale polarity cycle that these small scale magnetic features are tracing. So I'm going to close for the break by putting a really complex plot up. And I had a kind of bathtub epiphany moment here, where I was looking at this data and trying to figure out what it meant. Well, if you look at it in context, what's solar minimum in this picture? Solar minimum or sunspot minimum is right here between about 2008. There are 4 magnetic bands of opposite magnetic polarity around the sun's equator, separated by about 40 degrees, 80 degrees actually, plus the top to bottom. The ascending phase of the cycle only has 2 bands per hemisphere. And so there's something really weird going on about whether or not these bands actually modulate the sun's ability to make sunspots. I'm not going to put all this stuff up in here, but basically the suggestion is that the sun's ability to make sunspots is directly related to how the Hale cycles are playing out underneath them. That's quite orthogonal to the picture of Babcock and Layton, because, and I'll get into it in a little bit, but it basically means that those bands are interacting with one another and not just purely frozen into the plasma. So that's a kind of really controversial statement to end on the break, but this is based on 18 years of data as it was at the time. The behavior is linear, which means you can trace it out in time. And when we get back after a couple of minutes break, I'll take you on where that takes us to cycle 25 and what may be the underlying physics that is being revealed.
All right, thank you, Scott. I may have misread the schedule, but I think this is a good place to break. But before we do have one question from Prasad, who's asking about the relationship of these long patterns to torsional oscillations.
Wait a slide or two.
Okay.
They're identical.
Okay. All right. Then there you go. Is that
they're identical, which means you've got a manifestation of something in the outer atmosphere or something that's tracked in the interior too.
On the interior, right? Okay. And very good. Okay. Let's take 10 minutes break, unless if anyone wants to unmute and ask a question before we break, that would be okay.
I realize that's a lot of it.
Sorry, Dana.
Yeah.
Hello. Yeah, I didn't follow the answer. How are they identical? The bright point density is, how is it related to the torsional oscillations?
They map one another.
Oh, okay.
So
Okay,
yeah,
and
they're
is-
identical in their location and their timing, but they're not physically identical things. They're somehow related to one another.
But one may infer that they're related to one another.
Right, okay.
Yeah, they just, okay. All right, let's get back at the 10 minutes past the hour. And then we can do the last part. And the last part will then, because I hope, thank you for starting the recording, and we will take it over where we left off. And we're gonna find out more about solar cycle forecasting. Take it away.
Yeah, thanks, Dana. I hope you all had a refreshing break. I've recharged my coffee as if I'm by magic. So where I was talking to you about this idea of an extended cycle, and the fact that what we're really mapping out looks like the Hale cycle. So the sun's 22-year-long magnetic activity cycle, and somehow that contributes to the production of sunspots. Well, so we're not going to go into the how, but I'm going to show you a bunch of data to try and back up that point. And so there's a pretty famous guy around these parts called Dick Oltrock. And Dick Oltrock learned some stuff from other famous guys, including the guy that developed the first chronographs, who, as an interesting story, died on the way back from an Eclipse expedition in the 50s. They're always tainted. But what they did was they looked at the shape of the corona. And when they mapped out where the coronal streamers and the morphology of the global scale corona look like, you get a picture that looks like this. So if you kind of squint your eyes, you can kind of see that there's overlapping structures in here. If I look at the start of the time frame from 96 to 98, there's 1, 2, and then another one starts at high latitudes, mid-solar latitudes, then migrates slowly towards the equator over something like 20 years. That's not just from one spacecraft. That was SOHO, this is Stereo, this is Stereo B, and this is now SDO. So all the spaceborne imaging satellites show exactly the same thing in the extreme ultraviolet. So basically, the small scale coronal bright points, the large scale corona, as seen through helmet streamers and neutral lines, map onto what we discussed right before the break. So this idea of the torsional oscillation, or the speed up or slow down of the differential rotation profile within the sun. So you get a manifestation on something on the outside, mapping to something on the inside. And it looks a bit like this. This is just a schematic, of course, right? But what it does is it maps out roughly where those Hale cycles live, or where they are in the sun, as a function of latitude and time. Okay, so this is observation, an observationally driven model. It's nothing more than a cartoon, okay? And the colors are just to illustrate magnetic polarity and the position of the banded structure as a function of time. Okay, so there's another interesting feature that I didn't talk to you about in the first thing, is this idea, and I guess it's because I gave it a stupid name, the Terminator. It's getting a little bit of press coverage. But what it is basically when a Hale cycle comes to an end at the sun's equator, it seems to be a very strong trigger for the next solar cycle, or spots of the next solar cycle, to really get going. So I'm going to talk a little bit more about these Terminator events, and hope to convince you that we're really mapping out Hale cycles. And maybe at the end of that those Hale cycles actually do help you frame what's going on with sunspots, because we're going to reach a point where the resulting forecast for cycle 25 couldn't be more different from the one that's in the consensus that I showed a little bit earlier. So just to show you how effective this linear approach is, here's the data for EUV bright points and the magnetic scale circa 2013, with the projected bands linearly drawn out in time by my very able at the time 5-year-old. Oh yeah, does a pretty good job. They're tracking. So whatever's going on with these structures, it's linear-ish. And therefore, you can extend it out in time and study what epochs are going to do. So at the time, this said that we would be expecting the next death of a hail cycle sometime in around 2020, 2021. You can see the very clear example, or example of one in 2011. You see that the coronal bright point density at the equator goes to 0 in a heartbeat. It's green, 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 boom, gone. There's a similar event in 1997. And so the challenge is, what are those? But then what we anticipated at the time was we would start to see the first sunspots of cycle 25, probably in late 2019, as those bands near the equator start to cancel one another. This is, again, just an illustration. There's nothing more to add about that. But this is where your own critical thinking skills come into play. And critical thinking is really an essential skill in science in general. And, you know, the scientific method is really making critical assessments of the agreement between your hypothesis or model and the experiment or observation that you have. And so what do you do when faced with all this additional data? I'll let you read that for a second. And so I'm going to puzzle you now. We're going to now look at the contemporary data. We're going to look at the hemispheric sunspot number that I showed earlier. And we're going to look at the very recent butterfly diagram. Now, what is solar minimum? Solar minimum is sunspot minimum, okay? But it's the time when the sun makes no spots. However, if I put my hail cycle bands on this progression, there is 4 oppositely polarized magnetic bands around the sun's equator. What I'm speculating is that when the last hail cycle died in 2011 was the trigger that gave birth to the rapid rise or the significant rise of cycle 24. Okay, same can be said for cycle 23. The event appears to occur in 1997. I'll show you some evidence for that. But so what that means is solar minimum is a time of maximum cancellation. Okay, there's significant overlap going on between hail cycles, but there's significant overlap and cancellation going on, or some process that's inhibiting the ability for spots to emerge. That's more than likely some kind of buoyant phenomena given off by free flux, but I don't know really what Amitava and Dana talked to you about in the dynamo section. So when a hail cycle ends, the next cycle pops up. So, and what happens is that the sun's magnetic environment literally changes in a heartbeat. And for an object that's 4.5 billion years old, a heartbeat is about a rotation. That sounds a wee bit impossible, but let me show you an example. So in 2011, in fact, on February the 11th, 2011, the sun appeared to go through the last termination event. And this is just one of the coronal emission lines from Eve on SDO. And what it basically, over the course of one solar rotation, the extreme ultraviolet radiance goes up by 85%. So it just step functions up. It doesn't recover from that step function for another 7 years. Okay, that is basically a switch when it comes to a star. The interesting thing is to look at the response as a function of temperature for a similar type of event like this. So if I step through, if you remember some of the stuff about the solar atmosphere, if I go from cooler emission lines to hotter emission lines from bottom to top, all of the emission lines below about 1 million degrees show about a 5 to 10% change when a termination happens. But the coronal emission lines show a massive change. So basically, this corona switches on like wildfire. If you look at the same phenomena longitudinally, so now what you do is you basically take the daily data of your time series and prescribe a rotational rate. So every 28 days becomes 360 degrees of longitude, and you strap all the data together, you can now see that if I look through time in the Lyman alpha line, so the 1211 angstrom line of hydrogen, you can see that the switch on this terminator is extremely abrupt. So the atmosphere responds basically in one rotation. There's a similar analog on the back end. Might not get onto that, but there's actually a switch off too, which is quite curious. Just to illustrate a wee bit further what happens when you look at the epoch when we have 360-degree coverage of the sun, so from 2011 to 2014. Here's the terminator event as seen in bright point density combined between SDO and the two stereo spacecraft. And what you see basically is the bright point density in the equator basically drops by a factor of 2, while it increases in the northern hemisphere and southern hemisphere. And again, you'll see the rampant asymmetry between the north and the south. So the north gets going really fast. The equator drops, and the south takes quite a bit of time to get going. Now, I've showed you cycles 22 and 23 for the terminator events. They're not isolated, they're not distinct. You'll see here, this is the F10.7 radio flux, which is another solar proxy, but it really measures the response or the radio emittivity of the sun's corona. And as you can see at the termination points for the last Hale cycle, that basically the radio flux of the sun just basically doubled. If I put that in broader context and look back in time, you can see that all these termination events basically create step functions in the radio response. They all correspond to the main start of the butterfly wings from Maunder's butterfly plot. And so if you put them on this idea of a Hale cycle, you start to get this herringbone pattern of positive and negative fluxes going back to the 60s. So this is data constrained, right? This is still a cartoon, but data constrained. If I go back 140 years, I'm going to show you a trick. If I look at the observational record of prominences, so prominence is a structure that forms near a neutral line on the sun. So wherever you've got mingled oppositely polarized magnetic fields, you'll probably have a prominence or filament. That's not always the case, but these ones are basically what happens when you categorize or catalog the number of prominences or filaments as a function of latitude and a function of time. And these records go back to the dawn of H-alpha photography, so 1864. And so in the early 1900s, people were publishing papers about the progression of prominences and filaments with time, and actually documented the table, tabulated them, and started to discuss what they meant. And they look like this. So you can see the butterfly diagram in here, but it's a little bit more than the butterfly diagram because it goes back. It's extended over a period of time. And you can start to see the polar excursions in there again, and you can see that they roughly coincide with the termination events. Okay, so these polar excursions that you see, these are basically when the sun, they call it the rush to the poles, that basically the neutral line that goes up and reverses the polar magnetic field starts at a given point in time. As that neutral line marches towards the sun's poles, it forms a filament or a prominence, and you can track it. And if I only plot the highest latitude filaments in the system and the butterfly diagram, you can now start to see how things work together. Something remarkable in this, 55 degrees. So 55 degrees latitude seems to be the position where these filaments want to form, where they start. And they sit there for a few years before they migrate to the poles, but then they rapidly reform there. There's something very bizarre about 55 degrees latitude. That also came up in our bright point analysis and in the coronal analysis. So there's something really strange going on. 14, so observationally, using the sunspot record, we can go, and filaments, we can go back 14 cycles. And some of my colleagues will tell you that that's probably 14 coincidences of understanding what, or mapping out what these terminators are. And this is where David Hilbert comes to my rescue. We were challenged to develop an algorithmic approach, so a numerical approach to detect these termination events in the time series data, but also then to project when the next one would occur. And one of the things that we've noticed and we've been hankering for a long time was that the termination events themselves gave you some indication of how much overlap there was between the hail cycles. And if I didn't say it earlier, one of the earlier hints was that if there's more overlap between hail cycles, it gives rise to weak sunspot cycles. When there's less overlap between hail cycles, you get strong sunspot cycles. So it's like a big interference pattern. Not going to go into these plots in a lot of detail, except to tell you that when there's a phase jump in the Hilbert transform, so if you remember, if you know what a Hilbert transform is, it's basically a glorified Fourier transform that takes into account that the phase of the time series is not stationary anymore. And so it's like the next step up. It's like going to high school with time series analysis versus elementary school with Fourier transforms. And what you see is that the phase jumps. So you can see that these, when the time series go through a rapid acceleration, you get a phase jump, and that phase jump goes through one complete rotation. And those basically coincide with the terminator events. And so we can use this, we apply this trick, numerical scheme, to go back and identify the terminator events for times when we don't have imaging data. And we get a plot that looks like the bottom one. So it's like a herringbone plot with all these phase shifts. And the yellow dots are basically the observationally determined terminators. And so the numerical scheme does a pretty good job of what those of replicating those. And so I'm now going to get to the rub of what this means. So I'm going to do two experiments. I'm going to look at consecutive terminators, so the separation between terminator events in that record of 24 versus the upcoming cycle strength, so number 2, or the intermediate cycle strength, so number 1. So remember that my instinct tells me that when the separation of these two actually tells me about what's coming next. So the more that this terminator leaks to the right-hand side, it eats into the upcoming or the already at mid-latitude hail cycle and actually quenches its amplitude. However, if it shifts to the left and I have a short separation, I would then expect large cycles. So if I look at the intermediate strength, so experiment 1, there's no predictability. There is no information content there between the terminator separation and what's going on between them. But if I look at the terminator separation versus upcoming cycle strength, I actually get a quite nice relationship. Now, this is a pretty old slide because the same Hilbert analysis, like used as a predictive tool, and this goes back to Barrett and Niels Bohr, that predicting the future is extremely difficult. That cycle 25 looked like it was going to be huge because we were getting false readings from the Hilbert transform. But basically, this same approach would absolutely have nailed cycle 24's amplitude, and actually been not too bad with cycle 23, which is in there also. So we would have been in the ballpark for the other two predictions that we talked about earlier. In fact, we would have nailed 24. So the basic gist here is that hail cycles are present. You can observe them, they overlap, and they probably interfere with one another. The end of a hail cycle looks like a trigger event, literally. The death of one cycle leads to the very rapid growth of another one. The corona responds almost instantly. And that is out of date and wrong at the bottom, just wrong. But that relationship can be used to do what we call a hindcast, so the opposite of a forecast, where you take the information that you have and project it back through the relationship to see how well you would have recovered the past. And actually, it does not a bad job. So the red dots are the projected maxima of the sunspot cycles versus what we actually saw. And there's something to take home from this, is that it actually underpredicts large cycle strengths. So this the recipe that I showed you earlier actually under forecasts. And so now when I put that information together with the consensus forecast from cycle 25, you can see we're now starting to get into trouble. Because if you remember the consensus forecast for cycle 25, about 115, give or take a few. Our methodology is saying it's probably about double that. And so we have a very clean separation where the contrast couldn't be greater. Now it's up to you who you want to believe. But here's the present data. So the contemporary data up to this point, and you can see a whole bunch of data points on here, where there's daily, monthly, and monthly smooth data on this plot, versus the consensus forecast and that crazy thing that we put out there. So you can see that it's not dead in the, nothing's dead in the water yet, because the sun, as we know, likes to throw curveballs. But it would appear to be tracking higher than the NOAA forecast. So what is this telling us? Is it telling us something about the underlying physics of the star? Something that we've missed. But if we go back also to ulposiveness, there's a way to combat ulposiveness. It's not unique, but throwing more data at the puzzle. I would argue that a lot of the data that we're seeing and observing is actually indicating that the premise that Leighton and Babcock and others set up isn't complete. And because it isn't complete, that exacerbates the ill-posedness of the problem. What I mean is that because we are not using all the data available to us, we've actually limited our ability to understand what's going on and then predict what it's going to do in the future. And so there's something rather neat that I'm going to show you. And this is where Charles Tree comes in to the mix. And he was famous because he wrote this paper, Some Phenomena of Sunspots and Terrestrial Magnetism at Kew Observatory. So he developed an area of statistics called the superposed epoch analysis. And what that basically is if you know what your timescale is, let's say the Earth's terrestrial year, right? And you want to study what the weather in London looks like, you use that year as your calendar to understand what the weather in typical average weather in January, February, March, et cetera, are. So all he developed was a tool that once you know the underlying timescale, you can stack up all your data and analyze it statistically. But we're going to say this, do exactly the same thing, but we're going to use the Hale cycles as our clock, okay? So these termination points that we've determined, which are the end points of Hale cycles, we're going to put into our historical data analysis and try to recover whether or not this is actually a robust recurring signature. So on the left are my coronal breakpoints. Actually, this is the coronal intensity signature that I showed you earlier. On the right-hand side is the torsional oscillation from HMI and MDI. And as I indicated earlier, you'll see that those two characteristically are pretty much identical in terms of their progression with latitude and time. I've stacked them up versus the terminators, and you can get a rough idea, even from only 24 years of data, that it's the same underlying object that repeats and repeats. So just to illustrate that, with 24 years of data from SOHO, I'm going to slice through and perform a superposed epoch analysis to look at what the average 22-year window looks like. Okay, it's not a long time series. So I'm going to do the same thing for my coronal emission line data that was taken by Leo and others at the dawn of the chronograph age. So this is now tracking magnetic neutral lines in the global scale corona. Do you see the underlying pattern? So the global scale corona is repeating over a 22-year unit. If I take my 140 years of filaments and do exactly the same analysis, they stack up. So all of these things are tracking the Hale cycle, except for one. So to repeat this analysis with sunspots, and what do you see? Sunspots are collapsing statistically, but they only form half of the picture. So if I go through that and compare them all, you'll be able to see quite quickly. I'll let this run, and sorry that it's playing so quickly. You'll compare and contrast that the sunspots are only showing you half of the evolutionary picture of what's going on. Hence why, if you're only using sunspots to predict sunspots, it's going to be really hard to predict sunspots, right? That's a convoluted statement, but maybe there's more information out there to help you predict what the sunspots are going to do, because they're only a subset of the rest of the evolution. And now we get into the curious point. You remember earlier I talked to you a little bit about the Terminator and what it did to the corona. And I dropped a clanger that there's actually an opposite of the Terminator. There's something that happens on the declining phase. So if I show it 2011 and then again 2016, you know that solar minimum wasn't around until 2019. So there's something bizarre going on inside the sun when it comes to these Hale cycles that really, and if I should have put this in here, but they actually, if you put flaring activity on this, it also brackets that. So CMEs and flares are bracketed by these two timeframes. So February 11th, 2011, believe it or not, the first X-class flare of cycle 24 happened within one rotation of February 11, 2011. And the last one did, well, it occurred in September of 2017. But before that, the event switched off in September of 2016. So where are we now? How is this tracking? So remember, we're looking for an event like happened in 2013 in our Breakpoint record, where we prognosticated incorrectly that the Terminator was going to happen probably sometime in 2020. We were wrong. We almost got there around election day, so around November, but the sun didn't want to go the whole way. Only one hemisphere engaged. We're still waiting on this event, because having that event nailed down allows us to finalize our forecast for cycle 25, because we'll have the Terminator separation between 23 and 24. Remember also how it looks longitudinally. This is the really awful data from SOHO EIT that also shows the same phenomenology. It's an awful picture, but if I go back, you see this roughly the same phenomenology. This is the present data. And so in late 2020, you can see the evolution. Actually, you can see September 2016 in this data as well, where something weird goes on, where the equator actually grows in amplitude as the mid-latitude bands decline, something odd. But as we go on in time, you start to see longitudinal evolution, it's more active regions starting to kick in as a function of latitude. Now, when the Terminator event happens, this middle equatorial band will go red, will go to 0, or close to 0, and these two will start to light up in blue, green, and yellow patches. So we're actually building a website right now to track this. Slices through the EUV Breakpoint density catalog. This is present data. It was taken yesterday. We see again the massive overlap between the Hale cycles in this data. And so what we're basically looking for here is, again, this density drop at the equator. It hasn't happened yet, but the two bands of cycle 25 are very mature, but they will grow even more when this middle patch around the equator drops. Okay, so what we're really waiting on is this thing to decay. Another interesting point, if you remember from the last a few slides back, I talked about the rush to the poles. and that the polar migration appears to start coincident with the terminator. And we're starting now to see the polar crown filament forming at 55 degrees latitude again, and get ready for its march to the pole. So everything seems to be lining up. So these pink zones are highlighting the presence of the polar crown filament and the fact that it may be getting ready to march to the poles. So I'm going to have a lot of time for questions. I'm sure I've confused the living daylights out of a lot of you. And I'm going to wrap up by saying you need more information. Solar cycle prediction is an intrinsically difficult thing to do. And it's not. In the 1980s, people stumbled across this stuff. Okay, everything that I showed you in this talk is not new. It was identified in the 1980s, but they never tied it to sunspot formation. And maybe I'm crazy for doing so. They also didn't tie it to the Hale cycle phenomena, but they had all the observational records because I was able to identically recreate their analysis. For some reason, we are able to trace that 22-year Hale cycle. It seems to be recurrent and robust. Those Hale cycle bands have a very definitive end. We called it the terminator. We called it a million other things. It seems to be a trigger for growth at mid latitudes, and then for the process at high latitudes that triggers the polar reversal. Okay, that's really odd. So if you think about it, and remember the time scale that I said that this happens on. So I'm not trying to make Dana or Amitava's job any harder, okay, to explain this. But if you think about it, you've got a bomb or something goes off at the equator. Within one solar rotation, so 30 days, activity spreads across all longitudes at mid-latitudes, and then information is carried that makes that thing at 55 degrees latitude start moving to the pole. If you know about waves or physical systems, you know that they carry information from one place to another, and that's how it stays coupled. Now, the challenge is, what is that thing? Something is carrying information very rapidly through the star, right? That communicates the state of the magnetic system that allows things to happen. Now, I've been thinking about this a lot for the last decade, and you've basically been thrown into the deep end in the last hour and a half. But give that some thought. Dana may also think that I'm absolutely barking freaking mad thinking about this, because it's there's intrinsic difficulty to what I'm trying to say, and I'll get to that in a little minute. The terminator sees a rapid jump in all solar properties, right? X-ray luminosity. An old colleague of ours, Keith Strong and Julia Saba, published papers for cycle 23 and 2024 showing that the X-ray luminosity of the star jumped up by 4 orders of magnitude at one of these terminator events, right? 2 cycles. And so they actually identified that this was a predictor of something starting or something ending. So our old hypothesis was that the bands of the Hale cycle actually work together to shape the cycle. And so it's the interaction of those bands that's the really important thing. And if you want to worry about grand minima and things like that, it's the processes that are speeding up, slowing down the Hale cycle, which are very subtle, are responsible for those, because I can't really see that being any different. Now, if a terminator were to happen tomorrow, right? If Arnold Schwarzenegger were to walk in and go, "I'll be back," right? If that was to happen tomorrow, it would be about 10.5 years since the last one, not even quite, 10.25, which would put our prediction still about double the consensus opinion on cycle 25. That will still put it in the top 10 since records began. And I don't know if any of you are ham radio people, but this has got the ham radio people so super excited, because the increase in ionization as a result of the increased ultraviolet radiation actually makes radio signals from small handsets propagate further across the globe, so they can do these wacky competitions where, oh, they're not wacky, I guess they're awesome, where someone in Oklahoma is trying to talk to someone in Genoa, Italy over a ham radio, or further afield. So the challenge of the ham radio folks is to try and see how far away they can get contact. So if a big cycle comes, they might get that. They've been actually complaining, and ham radio numbers have been dwindling in recent decades because the sun hasn't been cooperating. So they're quite excited by this. But one thing to think about here is that, you know, and this is really my concern, the sun's been decaying for 3 decades. Okay, the amplitude of the cycles has been going down. So that makes this prediction even more, maybe either stupid or bold. But I would argue from an infrastructure standpoint, also the solar physics community isn't really ready for a big cycle. I think they should take advantage of it if it comes. But we've got so much new observant infrastructure between the Daniel K. Solar Telescope that you'll hear about, hopefully. Solar Orbiter, Parker Solar Probe, SDO, the list is long. That it's up to you guys to be the next generation of system scientists to put all this stuff together. But we need to get, we need to start thinking of the sun as a system. And so at that, I'm going to close with the last slide. One of the primary things that's been hurled at us about our conceptual Hale cycle, so this thing that we've been mapping out, was that it doesn't directly tie to the magnetic field seen in the photosphere. Okay. So if you worry about sunspots and cycles and things like that, you always want to go back and see if there's a verifiable magnetic signature of it. Now, we've implied small scale magnetic regions. We've implied magnetic neutral lines. We've implied global scale coronal magnetic structures which mimic the global scale magnetic field. But here is the last plot that I want you to look at carefully. So the upper panel is something that I've showed 15 times so far today. The lower panels are not. And the lower panels are broken up into 3, and they come from the Wilcox Solar Observatory at Stanford. And you can see the polar traces for the northern and southern poles. But in the middle of those is the progression of the sun's toroidal magnetic field as observed on the sun's disk for the last 40 years. Now tell me, does it look at all like the crazy conceptual cartoon thing that we have at the top? This looks to me like we're observing the Hale cycle. And so, and in fact, if you look at that Wilcox data, you can actually cleanly see the termination points, where the fact that basically where the toroidal field goes through 0 at the equator, if you track along the equator. So there's something intrinsically different about what we're saying. If I go back, I'm going to go scoot all the way back to here. Now, if the terminator happens soon, and we think it will, we'll be able to put that red curve on a final course. It may just be slightly bigger than the mean, but it's still significantly bigger than the consensus panel. My question to you guys is, what will happen next? I'm done, Dana.
All right, excellent. Well, thank you, Scott.